In this video, we will be discussing a fundamental element of mechanical engineering known as solid mechanics.
Solid mechanics is the study of the behavior of solid materials under unbalanced forces, temperature, and phase changes.
A tensile test observes the behavior of a material under the force of tension or a pulling force. Tensile tests relate to concepts in solid mechanics such as stress and strain. We will be observing stress, strain, Young's modulus, and Poisson's ratio through a simple tensile test. In this video, we will be using a ductile material, in this case, a strip of thin plastic.
In our tensile test, we will be observing two properties, stress and strain. Stress, or sigma, is defined as force over cross-sectional area. In this case, force is the force applied down on the plastic wrap, and cross-sectional area is the width of the plastic wrap multiplied by the depth of the plastic wrap. Strain is defined as the displacement over length initial. We define length initial as the length of the plastic wrap before it is stretched. In order to find displacement, we must measure the length final, or the length of the plastic wrap after it is stretched. We then take the difference of length final and length initial, which gives us our displacement. In our tensile test, we have both axial strain, which relates to the length of the plastic wrap, and lateral strain, which relates to the width of the plastic wrap. For lateral strain, we substitute length initial with width initial, which is the width of the plastic wrap before it is stretched. We find displacement by taking the difference between width initial and width final.
In this video, we are applying a force downward on our material. The more force we added, the more it's stretched. Since this is a ductile material, the material enters the plastic region almost immediately, and then stretches back with the slope of its Young's modulus.
As you can see in this picture, both the length and the width of the plastic had deformations. This demonstrates that the material went into the plastic region and holds true to what we know about solid mechanics involving ductile materials. An important element of any tensile test is Poisson's ratio, the negative ratio of lateral strain over axial strain. This is useful in solving for not easily measured deformations.
What we have written here is two stress-strain curves. The one on the left is the most general stress-strain curve, and the one on the right is a stress-strain curve that more accurately describes ductile materials. The one on the left, as you can see, has two major regions. There's the elastic region and the plastic region. The elastic region is the region where you can stress the material and it will return back to its original state. The slope of this line is called Young's modulus, which is the stress over the strain. The plastic region is the region that, when stretched to, it returns back with the slope of the Young's modulus to an area where there is a deformation. On the right graph describing ductile materials, you can see that there is an extremely small elastic region. So any kind of force that is applied to it will result in a deformation.
Our tensile test relates to the real-life example of a cable on a suspension bridge. Our previous stress and strain equations directly relate to the equations involved in the suspension cable.
In our diagram of a suspension cable, L is equal to length, D equals diameter, and F equals force. Using the equation, stress equals force total over cross-sectional area, we substitute total force as 2F, since there's F applied up and down, and divided by the area of the cable, which is pi over 4 d squared. Axial strain is given by displacement divided by length initial. Displacement is found by subtracting length initial from length final and dividing it by length initial. This simplifies to length final over length initial minus 1. Our lateral strain is found by displacement over diameter initial. Displacement is found by subtracting diameter initial from diameter final. This divided by diameter initial simplifies to diameter final over diameter initial minus 1.
This wraps up our knowledge and understanding of solid mechanics. As mentioned earlier, we can apply our understanding and apply it to a real-life application, like a bridge. This is important to know because if we were to engineer a certain object that was to undergo a lot of stress or strain, it would be very important to know how much the material can withstand. We would want to make sure that our material strength is sufficient for whatever application it may be. Thank you for watching.